Okay, so now we will discuss egress FQDN filtering. Let us start by explaining the problem statement. So let me just get the animation to work, and then I'll probably start explaining. So generally in any setup, really, in any network, you have private and public workloads. In a nutshell, public workloads are those that you want to expose. My apologies. Sorry. Uh, Public workloads are those that you want to expose to the internet, versus private workloads are those that you do not want. So a public workload could be your web server, could be any, I don't know, service, SMS service that maybe you're providing to the world, or any other service that people need to get to it publicly. Versus a private workload maybe is a database or a queuing system that is internal, that is meant to be internal only, meaning that you do not want people on the internet to get to that service, okay? So what this means generally is in certain clouds, they distinguish clearly a public subnet versus a private subnet. In others, they do not have a clear distinction. However, you're still able to achieve the logic of a public versus a private subnet. So these private workloads, and this is the focus of our discussion here, these private workloads, even though they are not to be accessed from the internet, however, they still need outgoing internet access. So they still need internet access in the outbound direction, right? Because these workloads need to be patched. They need some software updates. They might need antivirus updates. Maybe they need to get some code from code repositories, which are public. Regardless of the need, these workloads generally will still need to be to have outbound internet access. So you can think about them just like your laptops on the internet. Your laptops generally, unless you're doing something different, do not have, nobody can access your laptop from the internet unless you're doing some sort of port forwarding on your modems and you have public IP addresses or dynamic DNS and other stuff. But generally, your laptop is not accessible from the internet. But your laptop gets access to the internet. You can download updates, you can visit websites, you can update your apps. So this is what we are referring here to with the needing these private workloads needing internet access. So traditionally, CSPs had NAT gateways, and NAT gateways, all what they do is they take you to the internet. However, the problem is they do not constrain your access. They do not limit your access. So if you wanted to go to malicious sites or to bad sites and download malware, whatever you wanted to do, you had full open access to the internet, which obviously means a very high security risk that you need to be dealing with. And just to zoom in on what is happening here and how this works. So what in order to do it, you will have to configure on the route table of this private subnet. I'm referencing the RT. You will put a default route that points to the NAT gateway, and this will take the traffic to this NAT gateway. What the NAT gateway is doing is it is replacing the IP address of the workloads with its own private IP address. So I'm just going to give example. Let's assume that this workload has 10.2.2.2 and NAT gateway has 10.1.1.1. So what's going to happen is the packet, and let's assume that the packet we're looking at is from 10.2.2.2 to a Google DNS server, which is 8888. The packet is going to go to the NAT gateway. NAT gateway is going to do a source NAT, which means it's going to change the packet from being 10.222 to 888. It's going to change it to 10.111 going to 8888. And when that packet goes to the internet gateway, the internet gateway already has an EIP, which is an elastic IP that is mapped to the 10.111. So basically, the internet gateway is doing a static NAT where 10.111 will be changed to, let's assume, a public IP of 1.1.1.1. So which means that the outgoing packet will be from 1111 going to 8888. Okay, I just wanted to explain how this is working. And obviously, just to make sure I highlight this point, the private subnet cannot get out to the internet because it also does not have an allocated public IP address. So by going through the NAT gateway, now we have an IP address, and this IP address's importance is that it has a public address that corresponds to that private IP address. Okay, now that we've explained how this works, we still have a problem, which is unrestricted access to the internet, which means your workloads, if malware starts hitting, generally the way malware works is they want to connect your machines to some command and control centers on the internet somewhere. And once they get the connection, they can go and dig deeper into your environment and compromise your crown jewels and make a big, to be a big story and a very bad situation that customers have to deal with. Now, the traditional solution for this problem was to have a squid proxy. A squid proxy, if you've ever dealt like a blue coat or any form of a web proxy, what it does is basically takes the traffic. Again, we're going to have a default route that points to the squid proxy. And what the squid proxy is, it's basically you can have policies. It's able to inspect where the traffic is actually going, and you can basically define what URLs or categories are allowed and what others will be denied. Thus, we solve the problem of unrestricted access. However, it is a bit hard to manage, especially when you go when you need to scale. So if you have 50 VPCs or 20 VPCs where the internet is actually distributed and not centralized, imagine having to manage 20 proxies across, different situations and manage HA and manage their configurations. So it becomes a bit complex. The other option that's also there is to have a next generation firewall. However, for that simple problem, a firewall is generally an overkill and very expensive. Imagine having to go to your upper management to tell them that we need 20 firewalls because we have 20 VPCs that need access to the internet. Okay, so now that we've explained a bit the problem statement, we want to see how Aviatrix can actually solve it. So Aviatrix has, from the controller, we can launch a special gateway. We call it an egress filtering gateway. Think about this as a replacement of a NAT gateway. So we can have that egress filtering gateway, and the gateway, as other spoke and transit gateways, can simply be launched from the controller/copilot very easily and managed in the same manner. The interesting thing about the solution is because we manage routing within the VPC, we will make sure that the default routes will actually point towards that egress gateway. And then you can have the FQDN filtering rules, meaning, for example, if you want to allow them access to your antivirus, maybe to code repositories on GitHub, and a few other domains, we generally recommend a whitelist approach. A whitelist approach is where you decide that these domains are allowed and everything else is denied. versus a deny list, whereby you will have to specify only what is denied and everything else is allowed. So if you're looking for zero trust, you generally would have to follow the allow list. And again, after you deploy these filters and rules, they will go and render themselves on the gateways, and this way you have a central control, central management. You put your policies and they get pushed. What's also interesting is this works across CSPs, so you don't need to worry about any differences from one CSP to another. There are multiple design patterns when it comes to FQDN filtering. So there are some customers who only have that as a solution, meaning they're not running spoke gateways or transit. They just have the Egress FQDN gateway, and they use it as a way to basically put a zero trust policy across their workloads and limit what they can access to only what is needed. We also have the ones with again, distributed, meaning the internet is all distributed. However, they have spokes and transits. And finally, there is a model whereby you can have a centralized egress, meaning the internet is not on that VPC. The internet is centralized, so the traffic will go to the spokes through the transits, and then you have egress filtering gateways that will do the filtering and take traffic to the internet. It is worth noting also that the new model, though not there in the lab today, is that we can also, to limit the number of gateways that are needed, we are able to push to make these spoke gateways as egress gateways. So you will not need, again, in the future, those specific gateways. However, if you're running them, you can continue to do that. But these spoke gateways can be both your fabric, they can do the encryption towards the transit, they can do everything they do today. And then on top of that, they can take you to the internet and leverage egress filtering. We even have SSL proxy capabilities, IDS capabilities are there, and there is our distributed firewall as well. Okay. So this is, what I'm basically saying is you are going to have the same functionality and even much more without having to deploy these specific gateways. However, the labs have not been updated at this time. So we will leverage the Egress FQDN gateways for this, for the labs. So again, I explained that there are two models, one of them being the, let me just clear my annotations. One of them being the deny list model is basically you decide what you want to deny and everything else is allowed, versus an allow list model, which is the zero trust model, which is basically saying, I only allow this, everything else is denied. This is much better security generally. I'll show you even on the Copilot while we do the lab. There you can get stats. You can even look at the requests to see if the request has been allowed or blocked. Again, on the controller, you will have, you will basically have a policy, and that FQDN filtering will have a list of URLs that is allowed or denied. I'll show it to you in a minute. And then you will, once you have a policy, you need to enable it. And you can either choose an allow model or a deny model, and you need to attach it to a gateway or to a number of gateways. And this is where the policy will actually be rendered. Finally, on Copilot, again, we'll see this in the lab. You're able to have visibility on the rules, on the domains, and you're even able to see granularity on a per request level. Again, we'll see much of this on in the lab on Egress FQDN.